So we will start this afternoon section. We have two talks in the section, and then the first section is about the payment talk. We will speak about trapping horizon. Let's continue.
Thank you. I'd like to thank the organizers for inviting me to give a talk here. So I'll talk about my recent works about black holes, in particular the formation and evaporation of black holes, including the quantum effect of Hawking radiation. So let's start with reviewing classical black hole. This is the Penrose diagram for a classical black hole. So in the Penrose diagram, lines at 45 degrees are light-like. They are going at the speed of light. On the other hand, the notion of distance is ignored. But we have we assume spherical symmetry, so we have the origin r equal to 0 over here, and basically when you move forward in time, you're going upward. Here you have a singularity at the origin, but it's space-like. And at the end, you have an event horizon, and you trace it backward at light like 45 degrees. And it tells you that if you are outside the horizon, then eventually you go to this point. This is future infinity. And you will not be able to see anything that's behind this event horizon. Then Hawking realized that there should be Hawking radiation after you have a black hole formed. And then he just drew this Penrose diagram. I think it's a naive proposal. He actually said in his paper that since the Hawking radiation is a quantum effect, so it should have no back reaction on the geometry. So naively, he just put the classical black hole Penrose diagram together with the Penrose diagram for a flat space for the space-time after the black hole is completely evaporated. These two putting together, you get this diagram. On the other hand, this diagram is very strange because, for one thing, in the end, you still included the back reaction of Hawking radiation in the sense that the complete energy of the black hole is taken away, so you have no mass at the origin anymore. So that's a kind of back reaction. And also, in this picture, the event horizon is marked by the end of the singularity. On the other hand, we know that in physics, singularity is always to be resolved, right? If you have a UV complete theory, if you have a sensible theory, then you should have no singularity. So it's not clear what is the physical meaning of this singularity. And so nowadays, I think most people probably believe in this kind of Penrose diagram for a black hole. You have this part which is a high energy density region corresponding to the space-like singularity in the previous diagram, but it's resolved by UV physics. So you have some UV physics here that you can probably not describe properly in your low energy effective theory. But on the other hand, if you have the proper theory, you can describe its time evolution. So whatever state you have over here can evolve in time upward, passing through this high energy region. On the other hand, for the region roughly below this dash curve does not include any high energy events, so you can describe what's happening here in the low energy effective theory, so the geometry is perhaps similar to what we have in the previous diagram. But since there is no real singularity, so you cannot define event horizon anymore, everything happening in here can eventually come out to a distant observer. There is nothing that's hidden from people outside the horizon. On the other hand, you may have trapping horizon. I will define trapping horizon a little bit later. So from now on, let's assume that there is no event horizon. So when I mention horizon in the following, I would mean trapping horizon, or apparent horizon, which is just the time slice of the trapping horizon. By conventional model, I mean the viewpoint about black hole formation and evaporation, following the early works of Hawking and Davies, these people. So the standard model, not standard, the conventional model usually make the following assumptions. So, for example, if you talk about the static black hole, let's start with the static black hole, then the quantum energy momentum tensor would include a balanced ingoing and outgoing vacuum energy flux, both negative, but you have equal amount of negative vacuum energy going in and out at the horizon, so that the total energy under the horizon remains the same, so it's a static black hole. And since you have negative energy, so the no energy condition is violated. And then when you turn on dynamics, you talk about collapsing of matter. You have a dynamical black hole. And then there would be Hawking radiation. And it's then assumed that the Hawking radiation as a positive outgoing energy flow would balance with the negative energy flow for the static black hole, such that at the horizon there is no divergence. There is finite energy flux for free-falling observers. So the condition that for free-falling observers, they do not detect any high energy flow at the horizon is actually taken as a condition to determine Hawking radiation. And then, so in this picture, when you have Hawking radiation, at the horizon you have a small energy flow small energy flow out of the horizon, but you still have the same negative energy ingoing at the horizon as the static black hole. And because of that, the negative ingoing energy going into the horizon, the total energy under the horizon decreases over time. And so the black hole evaporates. On the other hand, the outgoing energy is detected only a bit far away from the horizon. And so that energy, outgoing energy, or the Hawking radiation, has no much chance to interact with the collapsing matter, so it's hard for them to carry information. In particular, there is no high energy event at the horizon in this description, according to the conventional model, so that throughout calculations, you can always use low energy effective theory. And therefore, you have the information loss paradox. So to reiterate, we have the information paradox for black holes in the conventional model because you have matter collapses into horizon, and you have outgoing Hawking radiation created a bit outside the horizon. And the black hole loses mass because of the negative energy going in. But the Hawking radiation has no chance to interact with the collapsed matter, so it's impossible for them to carry the information of the collapsed matter. So in the end, after the whole black hole is evaporated, you wonder where is the information of the collapsed matter. So one simple way out people have proposed is that the Hawking radiation does not persist till the very end. So in Hawking radiation is reliable, the calculation of Hawking radiation is reliable only when the black hole is very large. But when the black hole is very small, like a particle, you can no longer trust your calculation. So maybe at that time, Hawking radiation stops, and then you still have a remnant of the black hole. And perhaps all the information of the collapsed matter resides within this small remnant, this particle-like remnant of the black hole. This proposal is not very popular because you would then find problems in other aspects. For example, if you do have a particle-like remnant, you should treat it like a particle in your quantum field theory, but this particle has an infinite dimensional phase space, right? The internal degrees of freedom is arbitrarily large because you could start with an arbitrarily large black hole with arbitrarily large amount of information inside the particle. So when you put this particle in a loop diagram, you integrate over this loop propagating with this particle, you have an infinite factor. So this would invalidate all of your low energy factor theory. And also, of course, when you have the remnant with all the information of collapsed matter, you would violate black hole thermodynamical relations like Beckstein-Hawking entropy and so on. And also, of course, you would not satisfy the holographic principle because you have a tiny surface area for the remnant, but still a lot of information entropy inside. So the information loss paradox is not really just about preserving information, but rather how low energy effective theories and gravity and quantum theory can be put together consistently without contradiction to what we know or have tested already many times in quantum field theories. So to resolve the information loss paradox, the one crucial point is that we have the problem because there is no high energy event according to the conventional model. So low energy effective theory remains valid, and then in the low energy effective theory calculation, you don't see a chance for information to come out. So according to Mathur, some niceness conditions must be violated around the horizon. So one possibility is the firewall. But anyway, you need to have some high energy events to modify your low energy description in order for you to have a chance to solve the information loss paradox. So crucial questions: where are the high energy events? Can you find high energy events or not? Is the conventional model correct to say that there is no high energy events, or they have neglected some high energy events? Before we go on, let's make a comment. So there are different types of paradoxes in physics. Just in special relativity, there are two types of paradoxes. So we have the twins paradox. Twins paradox is essentially just how to say paradox because you didn't think carefully, right? So if you think carefully, there's no paradox. So you say you have twin brother and twin sister, they travel differently. So one stays on the Earth, the other goes in a rocket. Then they see each other as aging slower, but in the end, one of them is actually aging slower. But if you look at the space-time diagram, it's not perfectly symmetric. So of course, one of them can be younger than the other. There's no paradox. But we also have the barn and ladder paradox and Ehrenfest paradox. The barn and ladder paradox says that you have a farmer with a long ladder and a small shed, and or a barn, and he wants to put his ladder into the barn. So his daughter said, well, I learned special relativity. According to it, you run very fast, and then the ladder is going to shrink, so you can put it in the barn, and I'll close the door very fast. And the farmer starts running, but then he sees the barn to shrink, and he thought all the education is wasted. And in Ehrenfest paradox, you have a ring, and it's rotating, so you should have length contraction. On the other hand, in the radial direction, the radius is perpendicular to the direction of motion, so the radius is not changed However, in special relativity, the space is flat, so you should have a circle satisfying the ratio of circumference to radius ratio. But how is it possible? Right? So these two paradoxes actually are resolved only by noting that the property of matter has to be restricted by special relativity. So these two paradoxes actually imply that the consistent matter that can exist in a universe obeying special relativity are restricted. So I think one important issue about solving information loss paradoxes is to distinguish which type of paradox it is, whether you are just trying to do everything carefully and you can solve the paradox, or actually it's telling you your matter or the quantum field theories have to be restricted. So the task is this. We want to study carefully what is the geometry for a collapsing black hole, the time evolution for collapsed matter together with quantum effect of Hawking radiation, which is just vacuum energy for quantum field theory. And we want to include back reaction without ignoring the back reaction according to semi-classical Einstein equation. So by that, I just mean Einstein equation, but I include the quantum effect of the vacuum energy momentum tensor. And then we look carefully to see if there is any high energy event. So that's the task. And for simplification in this task, to carry out this task, we have some assumptions. Well, firstly, we assume semi-classical Einstein equation. If you don't believe in this, then I mean, it's fine. I think some people don't believe in this, but I think we do it step by step. So this is, in the beginning, we don't give it up. If we cannot solve the information loss paradox this way, maybe we should consider other options. But let's first consider this. And then we assume spherical symmetry, so that the metric of space-time can be put in this form, where I have the coordinates u, v, which are the two light-like directions in the radial direction. So u is going inward toward the origin at the speed of light, and the v is going outward. And then the spherical angular part is has the metric of a unit sphere times r squared, where r is called the areal radius. It means that when you are at this symmetric sphere, the area of the symmetric sphere would be 4 pi times r squared, according to this metric. Okay, it doesn't tell you that this radius is actually the distance between a point on the surface to the origin. That's probably not true. So r can be single valued or double valued or multiple valued. But sorry, I didn't mean that. I mean, when you are going out from the origin, the value of r can be increasing or decreasing. It doesn't have to be monotonic. It's single valued, of course. So we call this areal radius because it tells you the area of a symmetric sphere. And then we study, starting with static black holes, and then we turn on dynamics to look at dynamic black holes. Certainly the goal is to understand dynamical black hole, but we start with static black hole simply as an exercise to warm up. So then you wonder, why is this not done yet? I mean, people must have done many calculations. At least it's easy to carry out the perturbative expansion in the calculation. So you can start with the Schwarzschild solution, and then you turn on quantum effect. But you know that in vacuum, the only energy momentum tensor is the one due to quantum effect. So the semi-classical Einstein equation looks like this. so that the h bar factor of the quantum effect is multiplied to the coupling of gravity, 8 pi Newton constant, called kappa here. So expansion in h bar is the same as expansion in kappa. And so certainly it should be a simple task to carry out this perturbative expansion. But there is a point to pay attention to. The point is that although in this formula, kappa only appears on the right-hand side, so it looks as if the kappa going to zero limit, the zeroth order solution should be given precisely by the Schwarzschild solution when you get zero on the right-hand side. But actually, it's not exactly like that, because on the left-hand side, you have the Einstein tensor, which involves information from the metric. And the Schwarzschild metric has factors like these, which would give you powers of kappa when area radius r is very close to the Schwarzschild radius a, if the difference is linearly related to kappa. So then you get factors of kappa also on the left-hand side. And then you cannot say that Schwarzschild solution would be the good zeroth order approximation when the area radius is very close to the Schwarzschild radius. So in a small neighborhood of the horizon, the geometry can be significantly modified. So Schwarzschild metric is a good approximation only when your area radius is much larger than the Schwarzschild radius. But when you are very close to the horizon, you may have some important modifications to the metric. So we start with solving semi-classical Einstein equation for static black holes. And then you have this vacuum expectation value for the energy momentum tensor operator. But you have infinitely many different quantum field theories giving you infinitely many possible vacuum expectation values. So in general, you should pick a quantum field theory and then solve the Einstein equation. But that's too complicated. So one thing people often do is to assume that you have conformal matter, then using conformal trace anomaly, you know what is the trace of this thing. And then you also have the conservation of energy momentum tensor. Then you can partially fix the energy momentum tensor expectation value. In 2 dimension, actually, this is completely fixed by the trace and the conservation law. In 4 dimension, actually, you would still have 1 more functional degrees of freedom. So we actually studied the general case in 4 dimension, including that functional degree of freedom, assuming that it's regular. So together with Kawai-san and Matsuo Yokokura, we worked on the general case, assuming spherical symmetry and static solution. So the Schwarzschild background used to look like this, but we consider a generalization. So this is the most general static spherically symmetric solution. It has 2 unknown functions, rho and f. And we can expand them in powers of kappa on both sides of the Einstein equation. To deal with the unknown vacuum energy momentum tensor, what we do is this: we consider the most general solution to conservation law. So actually here, we don't have to assume it's conformal matter. So the most general solution is determined by the trace of the energy momentum tensor, and also you can think of the angular component of the energy momentum tensor. So then you can define this capital theta and integration of theta called g, and integration of the trace called h, and with hg theta. this is the most general solution to the conservation law for spherically symmetric configuration, static spherically symmetric configuration. All the other components of the energy momentum tensor vanishes. In addition to these two quantities, trace and the angular component, we have an additional parameter called Q. It's just a number. So this Q actually gives you a diverging factor in this TR coordinate system. And H and G actually, when R is approaching to A, they are also approaching to proportional to R minus A, so they do not contribute divergence at the horizon. So if you are zooming into a neighborhood of the horizon, the dominating effect is given only by this single parameter, little q. And then the near horizon geometry, depending on the value of q, could be one of the three possibilities, depending on whether q is less than 0, 0, or positive. So only when you have a fine-tuned value of q, which is exactly fine-tuned to 0, you would have the event horizon for the static solution. If q is negative, it corresponds to having negative ingoing, outgoing energy flux. You would have a geometry which is wormhole-like. If q is positive, corresponding to a positive ingoing, outgoing energy flux, you have no wormhole neck and also no event horizon. So let's give a picture of the first case, the wormhole-like neck. This is the case corresponding to the conventional model. As I mentioned earlier, for the static black hole, you would have balanced ingoing and outgoing negative vacuum energy flux. So by a wormhole neck, I mean this kind of local minimum in the areal radius. So this is a picture of space-time. This is the origin. So when you are moving towards the center of the spherically symmetric universe, you are always at a point at which you have a symmetric sphere. And when you are moving towards the center, the areal radius shrinks until you reach this local minimum. And then the areal radius increases again and it shrinks again. So typically when you have negative energy, you can create a wormhole-like thing like this. So if you have negative energy, you can pump negative energy into your apartment and make your apartment bigger on the inside. This is what happens when you have negative ingoing, outgoing vacuum energy flux. Here, we are not presenting the geometry very faithfully, because if you actually compute the proper distance between the neck and this point, which is the surface of the matter, then actually this distance is typically Planck scale, Planck length. On the other hand, the areal radius changes in a certain way, so it's impossible to plot the picture in 3D properly. So now we consider the dynamic case. You turn on time dependence, then you can just imagine how space-time geometry changes with time based on the static solutions. So you can either turn on time dependence as a perturbation, or you can consider parameters of the static solution to change with time. Or you can try to just solve Einstein equation directly. And we found correspondingly three types of solutions. So for the wormhole-like neck solution for the static black hole, when you turn on dynamics, you can have one of the two possibilities. Either the wormhole is evaporated together with the black hole or collapsed matter, or you can have the wormhole decapitated. By that I mean the neck shrinks to 0, so like in this picture. So you have a wormhole-like neck for the black hole, and as it evaporates, the total energy under the neck is decreasing with time. So at a later time, the total energy is smaller, so the neck gets smaller, because when you are looking at this thing from the outside, you should be looking at a smaller black hole with a smaller Schwarzschild radius. So it could be that the size of this bag remains large when the neck shrinks to 0. And in the end, you can have this bag detached if you have a transition of topology. Or maybe there is a small hole remaining. Then it would look like a remnant. So a remnant for a black hole should be interpreted as just having a small neck, but you still have a large internal space to keep the large amount of collapsed matter with all the information of the matter inside. Another possibility is to have everything evaporated together so that the size of the bag is shrinking together with the neck, and then there is no information left under the neck. So, sorry. Then, of course, you can also have the other classic static solution with no neck and no horizon, but just shrinking. So that would be corresponding to the KMY model, in which there is no negative ingoing outgoing energy. So if you assume that the normal energy condition is not violated, then you are essentially talking about the KMY model. If you assume that the no energy condition is violated, then you are talking about the conventional model, and you would have a wormhole-like geometry. Okay, so it looks like if you have a different quantum field theory, you can have a different scenario, and then the difference between these two cases probably depends on the interaction between the collapsed matter and the vacuum energy, the quantum field theory, degrees of freedom. So in the following, I'd like to talk about another thing, another topic, which is the general scenario for the conventional model. So I should say that for the KMY model, which I talked about a lot in previous years, for the KMY model, we know that actually the collapsed matter would never enter the trapping horizon. So all the matter stays a little bit at the Planck scale outside its apparent horizon, and Hawking radiation starts out from the surface of the collapsed matter, so it has no problem with information, no obvious problem with information loss. So therefore, the main question is about these two cases. When you have negative energy, do you really have to have information loss, or maybe we are missing something? So from now on, I would like to focus on the case when you do have negative energy. Still, we consider spherical symmetry, but now we consider geometries assuming the existence of trapping horizon. So with negative energy, actually, you can have trapping horizon. Without negative energy, you would not have trapping horizon. So what's trapping horizon? Trapping horizon for a spherically symmetric space, it's defined with respect to this area radius. So when you have light-like particles going towards outside or inside, in this or this direction, the area radius of the point could be increasing or decreasing. So for example, for Minkowski space, if you are going towards the origin, then the area radius is decreasing. If you are going outward, area radius is increasing. But when space-time is curved, you could have a trapped region, so that in both directions, the particles feel like the areal radius is shrinking, so that it feels trapped. In both directions, it feels like it's going inward in some way. And then, so you can define a trapped region, and the surface of the trapped region, or the interface between this kind of behavior and this kind of behavior, is where partial VR vanishes. We could have partial V squared R positive or negative, depending on whether this is inside this region or the other way. So if this is inside this region, when you are going outward, when V is increasing, you go from negative to, negative to positive derivative. It means that the second derivative is positive. So let's consider that case. This is the Penrose diagram. You have a trapping horizon. The internal space of the trapping horizon is the trapped region. The topology is typically like this because the trapping horizon has to be a closed surface because it's a boundary of something. And also it cannot include the origin because the origin is the minimal value of R. You can never go below R equal to 0. So it's never inside the trapped region. And so the trapped region is always like that. And then we mark the boundary of the trapped region, which is the trapping horizon, by its V coordinate. We call it V sub 0 for given U. So actually for a given U, you would have two values of V sub 0. So we assume that we are always focusing on this patch or this patch. And then the V0 is the V coordinate for this one or that one. From Einstein equation, you will be able to see that actually whenever the trapping horizon is, or apparent horizon is time-like, like this part, if the line is between U and V axis, then it's time-like. So this part is time-like and this part is time-like. Then TVV is negative, and when it is space-like, TVV is positive. This is from Einstein equation. I will show it a bit later. So the semi-classical Einstein equations is like this. On the right-hand side, it's the vacuum expectation value of the energy momentum tensor. And C and R are the two functions for the metric here and here. And you see that if you focus your attention on the small neighborhood of the apparent horizon, since partial VR vanishes at the apparent horizon, the Einstein equation is simplified. So actually you can easily solve some of the functions in terms of the energy momentum tensor by an expansion of the two metric functions C and R in power expansions of V minus V0. V0 is the location of the apparent horizon. So you can solve, say, R2, this coefficient to be given by constant times TVV, where the Planck length squared is just 8 times Gn, Newton constant. And the 0 superscript is referring to the value of the energy momentum tensor at the horizon. So R2 is the second derivative of R at the apparent horizon. And then you also have the trajectory of the apparent horizon, V0, and its time derivative, or derivative with respect to U, is given by this expression. So from the first expression, you see why we have this correlation between, from this first and second, you see that the sign for V0 derivative with respect to U is related to the sign of TVV. So, and furthermore, we mentioned that the second derivative of R at the horizon should be positive when you are talking about this side. So if you are on this line, then on the left-hand side it's trapped, on the right-hand side it's not trapped, so the second derivative of R must be positive. So it's telling, so it's telling you that R2 must be positive on that side, which means TVD must be negative. So it tells you that you must have negative ingoing energy in order to have a trapped region. And so let's be more specific. We focus our attention on this part of the trapping horizon because the other part of the trapping horizon may be residing in a region of high curvature. Maybe it's located very close to the center where you have high energy due to the collapsed matter. But on the other side, on this side, which is called the outer trapping horizon, can be associated with very large space with low curvature. So we focus on this part first. And so from B to A and A to D, this is outer trapping horizon, but we know that this part has a negative ingoing energy, and this part has a positive ingoing energy, according to Einstein equation. So we call this part the outer trapping horizon in vacuum, and this is the outer trapping horizon in matter. So the point A is typically the point where the surface of the collapsed matter will pass by. So you have collapsing matter, and the surface of the collapsing matter marks the boundary between positive ingoing energy and negative ingoing energy. So it passes through the point A. So you actually learn a lot about the relation between energy and geometry by considering the general situation. But the main issue is to examine whether there is high energy events. So what we do is the following. We first assume that certain no drama at the horizon conditions are satisfied. No drama means that there is no high energy or no large curvature at the horizon. So we focus our attention on these two invariant geometric quantities. With spherical symmetry, R theta theta is invariant. The residual gauge symmetry, when you have spherical symmetry, you can always pick this part. And so for this part, you have this gauge symmetry, and these two combinations are invariant under this gauge transformation. So you assume that the curvature is small, because you expect the curvature to be exactly zero for Schwarzschild solution. And if it's non-zero, it's because of the quantum effect, so you should have a factor of h bar, which comes with Newton constant, so it's always Planck length, like that. But once you make these assumptions, you can further simplify your Einstein equation, and then you see that the energy momentum tensor can be simply described in this way. So I pick a tangential vector of the trapping horizon to be called Kc, and its orthogonal radial vector to be called zeta. And this is time-like, this is space-like, I can normalize them. And then the energy momentum tensor, with that assumption of no drama, would always look like this, would always look like a light-like energy flux with the magnitude of curly E, which is given by this simple expression, regardless of which quantum field theory you consider. So this is a universal result. And also the important part is that the Newton constant, or the Planck length, is in the denominator. So when you take the classical limit when h bar goes to 0, this term actually diverges. Since the trapping horizon is a gauge invariant concept in spherically symmetric space, so this is a gauge invariant quantity. So you actually have a gauge invariant geometric quantity which diverges in the classical limit. So you have some high energy, gauge invariant high energy quantity in the generic situation without assuming anything about the quantum field theory. Now P is just this energy density multiplying the surface area, so it is the energy loss per unit time. So this is minus sign, meaning that you have negative energy going in. So the power of this energy is negative. And it's also given by a universal formula like that. So basically you have always, if you are staying on top of the trapping horizon, you would always feel like having this much energy lost into something. Actually, it's lost only because you have negative energy going in. Okay. So in Schwarzschild solution, you have a zero energy momentum tensor in vacuum, so all the curvature components vanishes. On the other hand, this particular combination, for example, where C is the tangent vector of the trapping horizon, gives you a T mu nu which goes to infinity in the classical limit. So it means that when you turn on quantum effect, at the horizon there's a discontinuous effect, non-perturbative effect with respect to the quantum correction. Well, then the question is whether this high energy this high energy quantity has any implication to the geometry. So we have shown that at the trapping horizon, you have a large correction, large quantum effect that we can define, which is gauge invariant. You can, of course, express it also as an order 1 geometric quantity, even though we express it as a 1/kappa energy momentum tensor. I should comment that this quantity is not completely local, just like Hawking radiation is not really local because you're comparing the vacuum state at two places, two limits. Here also, this quantity is defined with respect to this tangent vector of the trapping horizon, but the trapping horizon relies on the spherical symmetry, which is not a completely local concept. You have to go to the other side of the symmetric sphere to check whether this space has spherical symmetry. So it's not immediately obvious that this high energy quantity leads to large correction to the low energy effective theory. On the other hand, it would be interesting to study whether some low energy effective theories can have correction terms, no local terms, just like Hawking radiation terms, that would be sensitive to this high energy quantity. If there are such terms, then that means that for these theories, you would have a large order 1 correction to your geometry. So that's the end of my talk. Thank you.
In what sense you said it's not completely local?
In the sense that I'm defining this quantity in terms of the tangent vector of the trapping horizon, but the location of the trapping horizon relies on the spherical symmetry. You have to first know that there is spherical symmetry, and then you mark the trapping horizon. Yeah.
So the Hawking radiation, the energy moment tensor, is proportional to Newton constant or not?
Energy moment tensor is not proportional to.
Even it's where with respect to the background.
Yeah, so it's proportional to h bar. Yeah.
I see. So why you will think it back to the leading order, not back to the sub-leading?
Yeah, so the reason is that in the metric you have factors which allows you to have so yeah, so in the Schwarzschild metric you have such factors. So when you are very close to the Schwarzschild radius, when r minus a is of order kappa over a, kappa involves h bar, then you have h bar here and h bar in the numerator. So those terms would change the perturbative structure of this equation. So you cannot just drop the right-hand side. It would be inconsistent. Yeah.
Any more questions?